initial point. That is why these we can call it as initial value problem, differential equation with initial point. Similarly, a differential equation subject to the conditions at initial and other endpoint is called boundary value problem. The example. Suppose the second order differential equations, this is the starting point, this is at the point A, and this is the another point at x is equal to b. So the conditions of this differential equations at the initial point and other end point. That is why this is called boundary value problem. But when it comes to the differential equations, to find the solutions of the differential equations, its solution depends on what kind of conditions it is as per the physical situations. So that is why there are various types of boundary conditions. What are those boundary conditions? Dirichlet conditions. Why? This is unknown. Any unknown is given directly in terms of the independent variable or Neumann conditions. That means the normal conditions. What is the gradient of unknown with respect to its normal is a function in terms of x. This is called Neumann conditions. Together, we can call it as Robin conditions, Dirichlet conditions, and Neumann conditions. There is another kind of conditions, mixed conditions, and Cauchy's conditions. Mixed conditions is nothing but, see, suppose this is a domain and y is equal to f, and see, observe here, the combination of these two, both can be appeared. So one part is y is equal to f, and another part is c naught y plus c1 y with respect to its normality is equal to f. The Cauchy's conditions, it is a different along the same boundary. Along the same boundary, both can be defined. Dou y by dou n bar is equal to 0. This is called Cauchy's conditions. So like that, according to the physical situations, these kind of conditions can be taken. It takes place along with differential equations. Now the question is where these kind of mathematical differential equations can be arised. Here I am listing a very basic hanging cable, spread of disease, predator prey model. You can see here this is first order, second order, linear, non-linear, simultaneous equations. So there are different types of differential equations, but conditions is not mentioned because according to what parameters you would like to consider for the problem, the conditions can be varied. So that's why I didn't specify particularly for these models what the specific conditions. Next, with respect to partial differential equations, heat conduction equation, wave equation, Laplace, Poisson equation, transport equations, Schrodinger equation, and maybe suppose if we deal the concepts with fluid mechanics, there are Bernoulli's equation, Navier-Stokes equations, energy equation, concentration equation. It all depends on what context. There is no mandate of only the fluid mechanics, the solid mechanics, or maybe I would like to analyze the stiffness of the beam with respect to the civil engineering topics. Finally, these are examples for the partial differential equations. But for what, where these kind of differential equations can be arised? What are the different fields? because uh, finding the solutions of the differential equations, numerical methods, but the question is where you are able to get the differential
Okay.
manufacturing design. I'm just listing the information where these kind of equations can be raised. There are various fields to extract the differential equations. Now, the final ultimate goal is how you find the solutions of boundary value problems, which can be formulated from any physical model. So, this is called the mathematical model. For those mathematical equations, how you find the solution. Academically, we have seen that analytical solutions just have listed for free falling body, predator prey models. Those are a simple linear differential, ordinary differential equations. For those kind of equations, you can simply get the solution using analytical techniques, semi analytical, series solutions, transform techniques, numerical. So, if the problem can be solved or get the solution using the analytical solution, can implement. If not, with some approximations, we find we apply semi-analytical methods. The alternate is a series solutions like power solutions, Fibonacci sequence. There are different techniques to find the solutions of the differential equations under the series. Next, using transform techniques, Laplace transform, Fourier transform, jet transforms depends on continuity or discrete kind of domain. What kind of domain it is mentioned. Accordingly, we apply the transform techniques. And for that also, there are some restrictions. See these analytical series transform techniques. Each technique will have its own advantage and some restrictions to implement these techniques. If suppose the differential equation is not possible to solve using these three, the final we approach numerical methods. Numerical methods means approximating the solution. So approximating the solutions of the differential equations. There are many ways, different numerical methods to find the solutions of the differential equations. Let us see, just for your information, I'm just listing here under each analytical method, series solutions, transform techniques, what are all possible. So analytical perturbation, homotopy analysis, these two. Uh, Sometimes homotopy is a semi-analytical technique, and perturbation method also sometimes we call it as a semi-analytical method. It all depends on how many approximations you would like to find those. Accordingly, whether it is purely analytical or maybe semi-analytical. Next, series solutions, power series, Fourier series. Next, transform techniques, Laplace transform, Fourier transform, differential transform, integral transform techniques. Numerical methods. Just there are many, just I'm listing very famous methods. Actually, this shooting technique, it depends on Rangekuta fourth order method, any type of Rangekuta method. Now the finite difference method, finite element method, finite volume. So what we are going to discuss, that is a spectral method. And there are many numerical methods. Let us see what is the spectral method and who initiated these. The spectral method was developed by Stephen Orszag in 1969. First, before going to discuss about what is the algorithm, what is the main importance of this spectral method? It This technique can be applicable for any finite or unbounded geometry problems, and even for highly nonlinear problems. And using this spectral method, you will get the solution quickly, fast solution of steady state problems. For unsteady, it depends. Suppose the equations are coupled equations with unsteady. That means with respect to the time dependent equation. So the solution may not be fast. And computationally, it is a less expensive. That means that you can write the code for this algorithm in any language. There is no specific like based on the C or C++. There is no restriction like that. A few numerical methods can be implemented only in certain kind of programming languages with certain configurations. But the spectral method, it is a purely numerical method, no restriction for that. Whatever the system you take, you install any programming language like C, Fortran, MATLAB, Python, R language. But the thing is, you have to implement this step by step as per the algorithm. And for complex geometries, there is no guarantee of getting accuracy. And for discontinuous coefficients, for discontinuous coefficients. So this is disadvantage for these. And mainly these, what is the main advantage of the spectral methods? Any finite geometry, unbounded geometry. Here, unbounded geometry means why I specified here. Usually the people are dealing with boundary layer theory problems. So for that, the other endpoint is a infinity, 0 to infinity or 1 to infinity, whatever the starting point. The other endpoint is infinity. So that is the reason I mentioned unbounded geometry. When it comes to complex geometries means it is like, see, suppose let us take this is one side and like this the another side. These kind of geometries defining conditions facing a difficulty in writing a code. But algorithm wise, if suppose the differential equation is a very simple, then it is fine to find. But for these kind of complex geometries, is no guarantee of getting high accuracy compared to the finite element method or finite volume method like this. But whatever I tried for my problems, with my knowledge, I tried and I have gone through the available literature. With that point of view, I'm giving this statement. And I'm not telling it is not at all possible because the research, research means today we are facing one problem. The tomorrow someone come with solutions that can be implemented and can be followed by the other people. So with that reason, I'm just giving the statement that so for discontinuous coefficients and complex problems, is no guarantee of the accuracy using this spectral method. Now, how you are going to implement? What is the algorithm of this pseudo spectral method? What steps involved in this numerical technique? First, we approximate the solution using basis functions. We choose the collocation points. That means in the domain, If suppose, let me take, this is one domain, A to B. Because it is a numerical technique, we take some finite points in between. At these points, we are going to approximate the solution, whatever it may be. This just assume it is a solution of the differential equation. Suppose at these x naught or maybe x1, x2, and so on, x. Now the question is how you take these points in between the interval a comma b. Equispaced points or unequispaced points or any other choice to choose these points in between the domains A and B. That we are going to discuss. But there are many ways how you take it up. Next, define the residual expression, form the set of equations, convert that set of equations into matrix form, then simply find the solutions and express that solution graphically. That means we visualize whatever the solution we get for these differential equations. Then you compare with analytical, or maybe you cross check with what the valid parameter values of with respect to the physics concern. So that is important. Error analysis plays an important. Now let us see one by one how we are going to implement these for certain differential equations, what these approximates. The pseudo-spectral method, it is also called as a collocation method, but the question is, what is the main aim of this solving the differential equations? Let me take one differential operator with conditions at A and B, that is why boundary conditions. Let us take one small second order differential equation. Second order differential equation, this is, which is defined over the interval A to B with the conditions u of A is equal to alpha, u of B is equal to beta. As per the algorithm, first we approximate the solution. How we approximate the solution? What are the different ways? See, suppose let us take one set of the functions. These are called basis of functions, which which are considered from one of the vector spaces. Like the set of continuous functions forms a vector space. From that, I'm taking the basis, this phi naught, phi 1, phi 2, and so on, phi n. What are the examples for that? But with these basis functions, we approximate the solution y of x with these u of x. This is nothing but superposition principle. Linear combinations of these basis functions. Linear combination of this basis function. So any solution of the differential equation, first we are expressing as a linear combination of the basis functions. The question is, what basis functions you replace with these phi naught, phi 1, phi 2, and so on, phi n? What are all available basis functions? This is one of the basis, polynomial basis. This is one of the standard basis, 1, x, x square, x cube, x power 4, and so on, x power n. Then the solution can be approximated by this pi of x is replaced by x power I. This simply x power I. So where the Ci, these are the coefficients. We know x is a domain, Next, what other? This is a Lagrange polynomials. Lagrange interpolating polynomials. Maybe it is with 2 points or with 3 points or with 4 points. The number of points to be considered to take the Lagrange polynomials, it all depends on how you would like to implement this. Now the base is L0, L1, L2 and so on Ln. These Li is called Lagrange interpolating polynomial. So these solution can be approximated by this Lagrange interpolating polynomial. Next, Chebyshev polynomials. T0, T1, T2, T3 and so on Tn. Next, Legendre polynomials. I have not listed here. I'm just giving Legendre polynomials, Laguerre polynomials, cubic splines. There are different polynomials which can be considered in place of these to approximate the solutions of the difference. This is the first part. How we approximate this. Now the second point is choosing the collocation points. How you take the points in between A and B. So how you take the points between A and B. So it is suppose let us take n+1 collocation points. What is the main requirement in collocation means at these points, we are approximating the solution. Okay. See equispaced points, suppose. It is just like suppose the first point is x0, take the common difference h. So x1 is x0 plus h, then finally xi plus 1 is xi plus h. So the starting point is A, ending point is B. How many number of intervals? Then h is equal to B minus A by n. N is number of intervals, number of partitions we are taking for the domain A to B. This is H common difference. So the same thing, xj, A plus B minus A by n j, where A is nothing but x naught only. This x naught is nothing but A plus B minus A by n. This n indicates this is j by n. Some value. Keep changing that j value, we'll get what it is, equispaced. It is like next Chebyshev Gauss-Lobato points. This is whatever the domain A comma B. We are converting into -1 comma 1 domain. It is nothing but we are equating whatever the domain, or maybe we are converting the domain into -1 to 1 domain. We are changing the complete phase to another phase within the intervals, within the range of -1 to 1. Next, let us see for f of x is equal to 1 by 16 plus x square. With equispaced points, how you are able to approximate this? Or suppose if with Gauss-Lobato points, how we are going to approximate it? You can see right side is equispaced, the left is Gauss-Lobato. Keep on increasing the number of points in between -1 to 1. You just see how The solid curve is exact curve. The dashed curve is approximating with equispaced points, and the left one is with the Gauss-Lobato points. Now, you can observe initially we feel that with the equispaced points in between the domain, the curve is overlapping with exact one, but near to the endpoints, it is showing a drastic change, much variation between the exact and approximation. When it comes to Gauss-Lobato points, you see that how it is equivalent to exact solutions. How it is equivalent to exact solutions. So this is what is the advantage of taking Gauss-Lobato. What is the disadvantage of taking equispaced points? But I'm not saying that taking equispaced point is a disadvantage. It depends on the problem which we are going to handle it. It is not for all the problems. For few problems with equispaced points itself, you will get more accuracy. Now, for certain cases, maybe the solution is not getting with equispaced up to the required accuracy, then choose the Gauss-Lobato. So this is what is the difference graphically I would like to show. Next, let us see what is the next point, defining the residual. The residual is nothing but the error. What is the error? Now, when it comes to here, what is the error function? A second order linear differential equation, suppose we consider. Now, if we replace this u with approximate solution u of x in the differential equation, only the LHS involved u and which is approximated by this capital U. If we replace these, is there a guarantee of getting exactly whatever the right hand side r of x? Is no guarantee because we are replacing with approximation, but not exact expression, right? Therefore, these r of x, whatever the LHS, suppose L and R, LHS may be near to R or sometimes very far to R also. That is another case of discussion. Now, under these conditions, for these approximation, replacing in the LHS, if it is equal to R, it is fine. If suppose you take L minus R, then is approximately equal to G. This is called error. R is called residual. So LHS minus RHS. By after replacing U with approximating solution, that is residual. This is LHS part minus RHS. And these residual function, we have to write at every point in between x1, x2, and so on, x. There are points, right? x1, x2, x3, and so on, xn minus. At all these points, we have to write this. So that means how many equations we get? N minus 1 interior points. So you will get n minus 1 equations. This is how you define the residual. Suppose substituting these u of x, same. What is a u of x? U of x is summation ci pi I of x. The same thing we replace. Minus r of x. J stands for giving the information about spatial coordinate x. Spatial coordinate x. See, these provides n minus 1 equations because these residual is defined in between the interior points. But there are n number of equations, unknowns, because C1, C0, C1, C2, and so on, Cn. There are n plus 1 number of unknowns with n minus 1 equation. As we know, the property in algebra are may be related to the system of equations. Number of equations is equal to number of unknowns, then only there is a chance of getting a unique solution. So with that reason, how we get the other two conditions, because n plus 1 unknowns, these residual function will give n minus 1 equations. So two more conditions will be required. Two more equations will be required. That we get from the initial condition and other end. The same residual, we know that u is equal to same. U is equal to it is approximation solution. X is replaced with initial point, it is alpha. X is replaced with right end point, it is beta. So with these two conditions, so finally we'll get n minus equations, n minus 1, n plus 1 equations with n plus 1 unknowns, then we'll get this. Now, those residuals we have to convert in terms of the system of equations. You can see here, this is replaced with E minus alpha. You see the same E naught, LHS minus alpha. These will give one equation. This is at the point, starting point. Now the residual function will give n minus 1 equations. This will give last equation. These, which you observe here, it depends on Ci. It is just for your information, I'm writing C naught pi naught plus C1 pi 1 plus and so on Cn pi n minus alpha is equal to 0. Like that, these residual function with the different points will get n minus 1 equations. Write those n minus 1 equations along with the last equation which defined at the other end point. So these will give n plus 1 equations, and that forms n plus 1 equations like E0 0, E1 0, E2 0, En 0. Like this. This is the matrix form. What is the matrix form of those equations? Pi naught into C naught plus pi 1 into C1. It is a matrix product. Whatever the constant will take to right. Observe here the starting point alpha and ending point beta in the right side matrix or maybe vector. Replace these represents conditions at the initial point, at the end point. So now, what is A here? A is nothing but residual function. Just to precise for mathematical equations, just for representations. So it is difficult to type in this matrix for these big expression. That is why I precised it with some notation, and it is representing this. Whatever these expression is nothing but, you can see here. Yeah, this expression. This is nothing but capital Aij over. Yes. Now you can see that this is the differential system of equations in matrix form, and Ax r maybe is equal to B. Then how we find x? A inverse B, where x is nothing but this. Once you will get these values, C0, C1 and so on, Cn, replace in this. This is approximating solution. Okay. So now, first, I would like to try this methodology for the simple equation, step by step, how we are going to implement for simple problems. Let us see using monomial basis functions. Monomial basis functions is nothing but standard basis of vector space of the polynomials. Vector space of the polynomials. Let us consider one linear boundary value problem of second order. The conditions u at -1, u at 1, both is unit. Suppose its exact solution is exponential of x power 4 minus 1 by 4. What is the solution? First, we approximate the solution. To approximate the solution, we are taking one of the bases, maybe polynomials or Legendre or Chebyshev's or Lagrange polynomials. So one I would like to consider basically suppose monomial basic functions. That is 1, x, x square and so on, x power n. And these to approximate u with u of x. You see, approximate solution with these bases. This is the expression. And what is we need u double prime. That is why u prime j into x power j minus 1. Similarly, u double prime j minus 1 x power j minus 1. We replace this here. So what we get? So that is how you approximate the solution. Next, further step which is involved in this spectral method is choosing the points, location points in between the domain, whether equispaced or unequal spaced or maybe Gauss-Lobato points. But initially, I'm taking equispaced points. I request one of the participants, you please mute because it is a disturbance to others.
ఏం వాళ్ళందరూ వెళ్ళిపోవాలంట ప్రోగ్రామ్ అవుట్ చేసుకోవాలంటే వింటాం వాయిస్ వినపడిందా పొరపాటున యూనివర్సిటీ ఏముంది మావా అది మ్యాట్ ల్యాబ్ డౌన్లోడ్ చేస్తానా వీళ్ళందరూ ఇంట్లోకి వెళ్ళిపోయినారు
I'm sorry, may request one of you please mute and speak. It is disturbing to others.
ఓకే ఓకే బావ ఖచ్చితంగా సరే సరే బావ ఖచ్చితంగా ఓకే బావ
I request the organizers, please look into this matter, otherwise it is disturbed to others. Yeah. Now, how to choose the points in between these equispaced points? We choose the formula same, but the domain A is -1, B is equal to 1. We replace this, A is -1 and B minus A, 1 minus of minus plus, so that's why 2i by n, I is equal to 0 to 1. So this is equispaced points. So approximation got over. Choosing the points like as a second point, that is also got over for this basic second order linear boundary value problem. Next, we have to define residual error function. Because it is u double prime minus x power 6 plus 3x square into u. That is why this is u double prime is replaced. This expression is same and u with constant. And these residual function could be defined at in between points n minus 1, not from 1 to n. It is from 1 to n minus 1. That is why these gives n minus 1 equations. Next, two more equations from the conditions. Let us see what is the condition. U of minus 1 is 1 and u of 1 is equal to. This u is replaced by capital U of minus 1. Capital U of 1 is equal to. This capital U is nothing but Ci of x power I. So x is minus 1, then this is minus 1 power I. So it is simply C0 minus C1 plus C2 minus C3 plus and so on. This is what the starting condition gives, is equal to 1. Similarly, the right other condition, it is U of 1 is equal to. Let us see what matrix system resulting. I told right, C0 coefficient 1, minus 1, 1, minus 1, 1, minus 1. This is. Similarly, the right endpoint, this is 1, 1, 1, and so on. These in between Aij is nothing but residual function. The right hand side, you can see here, this is 1, this is 1, remaining all 0. Because in the differential equation, the right hand side is 0. That means no term which is independent of u. The independent of u term is 0 in the given boundary value problem. That is why in final matrix form, we are getting 0 except the starting point and ending point, 1, 1. Now this is nothing but Ax is equal to B. Ax is equal to B, and simply take x is equal to A inverse B. Then we'll get this solution. This is the graph. We know that, right? U at minus 1 is 1. This is 1. U at 1 is also is 1. This is by the spectral method, we are getting the solution. But this you can write, write the code in any of the, for these system of equations. You can feed these matrix in any of the programming language, irrespective of any size. Maybe 100 by 100, 200 by 200. Just feed in any programming language. Use this formula. X is equal to A inverse of B. Or otherwise, we know approximating the system of equations, approximating the solution of the system of equations numerically. Gauss-Seidel method, Gauss-Jordan method, Thomas algorithm, LU decomposition, Cholesky decomposition. There are many techniques to approximate the solutions of the system of equations. Or simply, suppose direct inverse of A into B is giving the solution. That means if B's matrix is a non-singular, then easy to find A inverse, then X is equal to it's simply the product with right hand side. Product with right hand side. If suppose this is not singular, this is not non-singular, then you go for numericals. So for even system of equations, for this also you need to implement another kind of numerical technique related to approximating the solutions of the system. Okay, so this is what the solutions got it. But the question is, how? What is the guarantee of this obtained solution is correct or not? That is the reason. Actually, I took the problem which is having the analytical expression, analytical solution, or maybe it is also called as a closed form solutions. With that closed form solutions, you can see exactly correlate. The solid is a numerical solution, that means blue, and dashed lines. These are dashed lines is exact solution. But I want to know, because any programming language visually, if two or three decimals equal, graphical representation shows overlapping the curve. We can't know exactly what is the difference of, maybe with three, four decimals difference, five decimals difference, six decimals difference. We don't know. That is why we need to take the difference of numerical and exact. Then what is that is absolute difference of exact and approximation. This is also called as the norm. This is also called as a norm. If we take these norm and drawing the curve for these norm, this we are getting. So that means you can see that these 10 power minus 9 and this is also 10 power minus 9, on an average it is giving 10 power minus 9 accuracy. That means after the point 8 decimals getting equal with exact solution. With exact solution, by considering 20 collocation points only, that means in between these -1 to 1, like this, we are taking only 20 partitions. Okay, if suppose we choose Gauss-Lobato points in place of equispaced points, that means this is the formula. Convert in terms of -1 to 1 domain using this function. It is just like transforming the coordinate system. If suppose a Cartesian coordinates, we convert in terms of polar or cylindrical polar coordinates or spherical polar coordinates, or maybe in any set of axes. The same way, the given domain we are transforming into these with these a new function zi minus cosine of pi. With this is the formula a plus b by 2 b minus a by 2 times of zi. This zi is replaced by this. If suppose you are not taking a negative, your solution will get like this. So this is a meaningful or meaningless. Just imagine. That is why that mind, but both ways fine. After getting the solution, how you are write the program to show the visualization of the solution. Next, with these Gauss-Lobato points, as we discussed, this is of course exact correlating with exact solution. But what is the error? What is the norm behavior at different points? Earlier, with equispaced points, we got 10 power minus 9. Here, it is getting 10 power minus 12, which is giving less error. 10 power minus 2 is less. That means Gauss-Lobato points gives more accuracy. Equispaced points gives more error than Gauss-Lobato points. But observe here, these all with monomial basis functions only. Next, using Lagrange polynomials. This is with monomial basis functions, 10 power minus 12. With the Lagrange polynomials, it is getting 10 power minus 13. That means one more order is increased. Accuracy, one more order of accuracy is increased. Next, Suppose with another numerical technique, actually the same problem with the 20 step sizes points, we are getting 10 power minus 6 accuracy only. You can see here, this is mono polynomial equispaced, monomial polynomial Gauss-Lobato points, Lagrange polynomial with Gauss-Lobato points, and sorting technique. So even with monomial polynomials with equispaced points itself gives more accuracy than the sorting technique. So this is what is advantage of the spectral method. Now the same thing, solution using Lagrange polynomials. This is collocation points, the same, whatever the equispaced points we are considering are Gauss-Lobato points. Now solution using Lagrange polynomials. How you are going to take the Lagrange polynomials? So we know that if you take the you divide the points, it is x naught and so on xn. There are L naught, L1 and so on Ln Lagrange polynomials. At these Lagrange polynomials L naught, x naught, at this point is this will give 1. This L naught polynomial at these x1 point will give 0. Gives 0. So this function gives either 0 or 1 according to the Lagrange polynomials. That can be replaced with this approximating function. Then choose the collocation points. Next, like this. And its derivative. How you are going to find this derivative? U prime. This is u of xj into pi prime of x. But we have to convert these derivative at these points in terms of -1 to 1. The same thing, u prime of x, pi j prime of x, u of xj, that convert into matrix form. Now this is u derivative in vector form d times of u. This d is called derivative matrix. This is called derivative matrix because these derivative at all these points we have to find 0, 1, 2 and so on n. That is why we are getting matrix. And these, suppose a double derivative, again you will get, this is called a d square, is nothing but double derivative, second order derivative. If suppose nth order derivative, that means nth order derivative will get d power n, like this. So u prime with at different points d 0, 0, d 0, 1 and so on up to d 0 n. Then changing the index with respect to row and column as just specified d into u. And similarly, this is the algorithm of writing the derivative matrix for the Lagrange polynomials. Then u prime du, u double prime is a d square u, u triple prime is a d cube, nth order derivative is a d power n into u. This is just like recurrence relation for any order of the derivative. It is a recurrence relation formula for the any order of the derivative to use in Lagrange polynomial basis functions. That is why C, higher order derivatives can be obtained as like this. But what is a D means? D can be defined like this. If I is not equal to J, if I is equal to J, if suppose I and J both are 0, what is this? Or maybe at N, what this value? We are defining these as per the concept of Lagrange interpolating polynomials. Now, with these Lagrange interpolation, same. So this is one equation, second order equation, taking the short form of these derivatives, approximating these with these polynomials. Now see, this is one after another. At x0 point, at x1, at x2, and so on at xn. At different points. Now, what is the matrix? U of x0, U of x1, U of x2, and so on. U of x. Next, where aij, it is a residual function. Now, this first row and last row can be replaced with conditions. This is how you are getting these diagonal forms, where A is equal to, because this pi double prime itself gives one more matrix form. This is a D square, and this is derivative matrix. If suppose the first two terms are derivative matrices, these also we have to convert in terms of matrix. This delta ij is nothing but identity. What is the identity matrix? If row and column index is same, then it is 1, otherwise 0. That we are representing with Kronecker delta. If I is equal to j1, otherwise 0. What is the delta ij? This is 1 if I is equal to j, otherwise 0. That is why it is just kind of identity matrix. That same d square, first derivative, 2 times of u. Here identity. That is why here 2 into I, identity matrix. And these, what is a capital A naught d square, A1 d, 2 times of I. This is A times of u is equal to 0. Because there is no term which is independent of u. That is why the right hand side we are getting 0. And why we are writing A naught in terms of a diagonal matrix? Because if these 1 plus x naught square multiplied with diagonal element only, otherwise that becomes 0. As per the concept L naught of x, L naught x naught only gives 1. L naught at the other point will be 0. L naught at the other point will be 0. With that reason, these terms will get 0, only diagonal expressions. A naught is nothing but whatever the second order derivative coefficient in terms completely constant, or maybe in terms of x. 1 plus x naught square, 1 plus x1 square, 1 plus xn square. Similarly, the second coefficient, here only the constant 2. So no need to worry, because it is multiplied with I only, identity matrix. This is. Now, as per the initial condition, u of minus 1, this is 1, remaining all 0, is equal to 1 by 2. So right hand side is 1. Next, u of xn, this is 1, remaining all 0. Remaining all 0 is equal to 1. In the differential equation, no term which is independent of u. That is why these are all 0. So this is, what is this? AU is equal to K. K is nothing but this. Then U is equal to A inverse. You see, with 10 Gauss-Lobato points, we are taking a less number of points here. although we are getting 10 power minus 6 because this Lagrange polynomial concept. Because of this Lagrange polynomial concept. See, error graph using monomial polynomials for the same with 10. Earlier we did with 20 equidistanced points, but this is with 10 and this is 10 with Gauss-Lobato points. We are getting 10 power minus 9. This is also with monomial polynomial only. Next, solutions of PD. How we implement the spectral method to find the solutions of the differential. Let us take a simple PDE. It is a partial differential equations operator in terms of x and t, whether t is time variant or maybe other spatial coordinates. It depends on what physics we are considering here. Now these are the conditions. And the initial condition when t is equal to 0, this is we are taking as initial condition, and these are all we are treating as boundary conditions. Now this is one standard parabolic partial differential equation P, Q and R. These are all continuous functions. This PDE can be solved with the conditions. This is the initial and the other boundary. The procedure is same. Approximate the solution, choosing collocation points, residual, form the set of matrix form. After finding the solution, express that solution graphically. Visualize it, what will get it. Now here, how you are going to approximate, because the partial differential equation where the independent variables are two. One is in terms of x, another is in terms of j. That is why I index function x, j index with respect to t. And these bases, both you can take with a monomial basis only. 1x, x square and so on x power n, 1t, t square and so on t power n. And these similarly suppose Lagrange polynomials in terms of x and in terms of t, or maybe Chebyshev, or maybe legendary polynomials with respect to which spatial coordinates you would like to take, that it is. And similarly, collocation points. When it comes to collocation points, you can see how we are taking the domain. Maybe this is x and this is a t. So this is a starting point x0 and this is xn. So next x1, x2, x3 and so on xn. So this is a starting t0, t1, t2, t3 and so on the last. At what exactly end of the t you are going to find solution. So the solution at this t1 depends on this t0. The solution of these depends on this. Solution of these depends on this. It is just like that is what we implement in finite difference method. But in this case, it is not like that. We are approximating the solution in terms of x and t. All together, we are replacing in the differential equation, writing in terms of a matrix form, then finding the solution. Now, you may have a doubt with respect to x and with respect to t, how we get the matrix form. What is a constant vector? What is a solution vector after converting into the matrix form for these kind of partial differential equations? Let us say same. The formula is same. Here also a plus, but it is always start from 0. T interval belongs to 0 comma t, right? So that is why the starting point a becomes 0. That's all. Is no much further information about it. Or suppose for Lagrange, we are using Gauss-Lobato points. This is Gauss-Lobato for the time and for spatial coordinates. Or maybe both spatial coordinates. In place of t, suppose y, you can take this is x and this is y. X and y. These two are spatial coordinates. By this picture, you will get to know what exactly the discretization of the domain corresponding to the solution. This is U00, U10, U20. That means Ux comma t. This is T0. T is equal to 1, T is equal to 2, and so on. T is equal to m. This is X0. X is equal to 1, X is equal to 2, and so on. X is equal to n. Now, converting this is a collocation points, residual function, partial differential operator with approximate solution minus right hand side with the boundary conditions at the initial point. See here, initial point when y is equal to c and y is equal to d. Next, boundary conditions when x is equal to a and x is equal to b. Why it is y is equal to c, y is equal to d means this is x is equal to a, x is equal to b. This is y is equal to c, y is equal to d. So there are 4 boundary conditions with these residual. We get nx plus 1 into ny plus 1 number of equations with these conditions. That many unknowns and that many equations we get from these matrix set of equations after converting into the matrix form, after rewriting the set of equations from the residual and based on the conditions. Let us take one simple linear PDE with initial and boundary conditions. With initial and boundary conditions. U of minus 1 comma t, U of 1 comma t. This is the exact solution just for verification how we get whether it is exactly getting same or maybe if suppose any error means how we need to rectify it. So that is why we are taking a simple problem which is having exact solution. The same procedure what we implement to ordinary differential equations, C x power I t power j. Next, with respect to x derivative, I into x power I minus 1. With respect to x twice, I into I minus 1, x power I minus 2. With respect to t, j into t power j minus 1. Next, choosing the points, equispaced points, basic topic, monomial polynomials, equispaced points. With that, we are trying to implement and understanding the top, what is the spectral method for PDE. Then we extend to high geometry problem or high complexity problem. So the same with the given conditions because the conditions is minus 1 to 1 and 0 to some extent. So this minus 1 plus 2i by n, tj is j by n. Next, residual function. Because this is with respect to t first order, with respect to x second order and this. And these we replace in this second order This is with respect to t, and something here it is missing. Then in place of here it is I minus 1. This is the first order and E. So LHS minus RHS or RHS minus LHS is equal to 0. Either one you take. This is the result. Now the conditions. When x is minus 1, this is condition. So e power t. Next, when x is equal to 1, e power t. Initial condition when t 0, this is the expression. This is the same procedure. These you convert into equations, and those equations you convert into the matrix form. Then you will get the matrix form. And here, first you observe here, this is when t is 0. It is already given in the problem. This is at t is equal to 1. You will get this solution. When t is equal to 2, you will get the another solution. When t is equal to 3, you will get another solution. When t is equal to 4, 5, 6, and so on, this. So at different time coordinate or maybe t coordinate, you have to run the program with a matrix system, then execute the solution and feed in this matrix. So for that, we are getting the solution line. But it is difficult. That is why at one point of t coordinates, if would like to compare with exact solution, it is exactly correlating. That means it is giving accurate solution. But up to what level it is giving accuracy, that we need to check. That is why error approximations. So it is giving 10 power minus 4 with 10 spatial coordinates, 10 collocation points with respect to t. If we consider Gauss-Lobato in place of equispace, we are getting 10 power minus 6. So this is how we implement spectral method for solution of linear ODE and PDE. The same thing you can extend to whatever the PDE, which consists of 3 independent variables or 4 independent variables or 5 independent variables like that. This is a spectral method for solving ordinary differential equations and partial differential equations. This is only for linear. When it comes to non-linear, is there time?
Sir, you can, sir. You can, sir. You can proceed, sir. No
Yeah,
problem.
yeah.
Participants are ready to listen.
Now, the nonlinear differential equations, how we handle these nonlinear differential equations. So we till now we came to know that finding linear ODE or PDE using spectral method. But for nonlinear differential equations, whether it is ODE or PDE, how we handle this? First, we convert these nonlinear differential equations into linear using quasi-linearization method. What is that quasi-linearization? It depends on Newton's method, or most often we are calling as Newton-Raphson method. Same. So let us see, this is a function in terms of 3 variables. Those variables we are representing with y, y prime and y double prime, where f is nonlinear operator of y of x and its derivatives. How we convert? Using Taylor series. Expand this f in terms of three variables. It is just like f of x, y, z. In place of x, y. In place of y, y prime. In place of z, y double prime. So Taylor series expansion of this function in terms of three variables. What we get? Let me write simply just for understanding. So what you will get? F of x, y, z about the point ABC, suppose. It is just like f of ABC plus x minus a into derivative of f with respect to x, y minus b derivative of f with respect to b, z minus c derivative of f with respect to c, 1 by 2 factorial second order, 1 by 3 factorial third order, plus and so on. Okay, so let us neglect this because x is approximately a, y is approximately b, z is approximately c. Then here you will get second order powers. Here you will get third order powers. Suppose if we neglect these, till the first order, suppose. So what you will get? Sorry. Yeah. Now this is f of x, y, z, a, b, c is nothing but times of gradient of f dot product. The same thing it is mentioned. Y minus yr, y prime minus yr prime, y double prime minus yr double prime gradient f is equal to g. Neglecting second power from the second powers of difference x minus a like this y minus yr, y prime minus yr prime, y double prime. This is the gradient. Now let us see this value becomes 0 and what we will get this. Just notation wise y of x, y power 0, y dash notation. These are the notations we are taking. Compact form of the quasi-linearization method after r plus 1 iterations. This is yr plus 1p, yrp. This is right. In place of y, we are taking yr plus 1. That's all. There's no much difference here. R plus 1. Now this is yr plus 1. This summation is nothing but this is x minus a dou f by dou x, y minus b dou f by dou y, z minus c dou f by dou c, like that. It is a short form of that. Now it simplifies into this form. A to r, yr double prime. This is yr plus 1, yr plus 1 prime, yr plus 1 is equal to r. Because this is differentiating with respect to this, right? P. P stands for derivative. If P is 0, only y. If P is 1, first order. If P is equal to 2, second order. That is why accordingly it is y double prime, y prime and y. What is this r of x? This r with suffix r. It is just like how we take Newton-Raphson xi plus 1 is equal to xi minus f of xi by f prime of xi. This is completely in terms of xi, known values. This is the unknown. Like that, all known values at the rth level shifting to right side. And what is these coefficients? A2, A1, A0 is dou by dou y as per the P. This is APR is nothing but this. Now, according to this Finally, this R of x is nothing but complete these with respect to the R minus this function. Complete this expression at rth level minus the given equation. This is F. Now observe here, this is called linear form. Whatever the nonlinear form, based on these Taylor series concept, converting into the linear form, those coefficients with respect to the derivative, who can represent those. This is called quasi-linearization method. Let us see for one nonlinear ODE. This is y double prime, y prime minus y cube. There is a nonlinearity here. Y cube is also nonlinear. And these, how we convert into the linear? Because the second derivative, start with second derivative, a to r. See here, in place of this, you take any notation. If you want to take a, y r plus 1 double prime. This is b, y r plus 1 prime. This is c, y r plus 1. Just for convenience, I took a 2 r because the second order, a 1 r because the first order, a 0 r because order is 0. So function itself and r of x. Simply I'm writing this nonlinear into linear form. Now the question is, what is a2r, a1r, a0r? How we are going to find a0r? That means equation differentiating with respect to y. Differentiating these with respect to y. So y prime minus 3y square. That's all. Y prime minus 3y square at rth level. Next, a1r with respect to y prime differentiation. So with respect to y prime, only y at rth level. Similarly, a to r with respect to second order, it becomes. Now this is nothing but the same. What is this? A to r y double prime at rth, a1r y prime at rth level plus a0r y at r minus the equation at rth level. This is F. So it is complete. See here, this is the differential equation. Sorry, a to r is yr prime minus 3yr square into yr into yr prime 1 into y double prime minus the given equation. So these two will get cancelled. One yr prime get cancelled. So finally what will get? This is this product and minus 3, this one. What will get? 2yr. So this is capital. You see, finally, what will get? This is linear form. Now, this is nothing but you just see that it is capital A of x into y double prime, capital B of x into y prime, C of x into y is equal to some function in terms of x. Now, this is a differential equation, right? Double derivative. First derivative y. This y can be approximating with basis functions. And then choose collocation points, whether it is equispaced or Gauss-Lobachov points. Define the residual function after replacing this y in this linear form. At different points, write this residual function to get the different equations, and with the given conditions, implement this. These are the conditions. Approximate solution is obtained by solving above equation at rate. Solution. But here, this is unimportant because this is xi plus 1 xi minus f of xi f prime of xi. What is the x naught? That means what is the solution initially you are taking? You take any expression of these such that satisfying these given conditions. Satisfying these given conditions. That means what conditions are given? Y of 1 is 1 by 2, y of 2 is 1 by 3. Satisfying these two conditions, you choose any function. So just randomly I'm taking this. If suppose x is 1, if x is 1, 2 by 3 minus 1 by 6. So you'll get 3 by 6. Then that 3 by 6 is nothing but 1 by 2. This is 1. If x is equal to 2, 2 by 3 minus 2 by 6. So you'll get 1 by. So like that. You can choose any expression which satisfies the given condition. This is at r is equal to 0. Now we need to find at r is equal to 1th level. See, same approximate solution with monomial polynomials, equispaced points, residual function. But here, what is the other additionally we are getting here? Rth level. Here rth level, here rth level. If a linear means this rth level should not come. Forming set of equations, writing a matrix form and then find the solution. The remaining procedure is the same. So this is the solution. So what is the error? 10 power minus 10 comparing with exact solution, absolute difference of approximation and exact. See the coupled systems, how you are going to find. This is actually I took from one of my research papers. You can see here f, theta and phi. These are going to find. These are the unknowns. You observe here the product non-linear. There is a product non-linear. F prime square product non-linear. This is a non-linear. And this product with unknowns. This is also one non-linear. That is why these first we convert into linear using the quasi-linearization technique. The same because here fourth order derivative, same fourth order like this is equal to R. We find this what is alpha 114 derivative of this with respect to fourth order derivative of the equation. So here differentiating these with respect to fourth order derivative, what will get? Its coefficient is 1. That's why you will get this is 1. Like that. We are going to find all these coefficients and then replace in this. Accordingly, we find R1, R2, R3. Then monomial polynomials for f. Ci x power I, di x power I, ei x power I. Okay. So here what we get, the matrix form. Is equal to right hand side. Right. So first we get, you observe here Ci. That is why it is C0, C1 and so on, Cn. Next the coefficient is a di. So d0, d1 and so on, dn. Next E, E0, E1 and so on, En. So we'll get block matrices. We will get block matrices like this. Now the question is, which block matrix relates to what? So this is related to F. This is related to F. This is related. This is G. G and H. H. I'm sorry. Is theta. This is 5 unknowns. But the first row black matrices getting from the first equation. This is from the second equation. And this is from the third equation. Now the completely Ax is equal to B. So suppose these I will take it as, maybe these I'll take it as A11. This is A11, A12, A13, A21, A22, A23, like that. So, and these same, choosing the collocation points for all, find the residual function for first one, second one, and third one, and converting into the matrix. This Ax is equal to B. Same here also, X is equal to A inverse. Okay, but the question is, in these, this is the solution, right? Only this part related to F, and this part will be related to theta, and this third part will be related to pi. And for that, see, this is F solution, theta solution, pi solution. Okay, so this is how we are going to implement spectral method, either linear or non-linear, or maybe ordinary differential equations, or maybe partial differential equations. I'm not giving the explanation for non-linear PDE, but the procedure is the same. But so what we covered in this, first, what is a boundary value problem? What are the different types of boundary value problems according to the conditions? What are the possible fields to get these kind of boundary value problems? What is the spectral method algorithm? What are the various possibilities can be considered, and in each step of this algorithm with respect to basis functions or maybe collocation points, convert into the matrix form, whether you will take the inverse of the coefficient or maybe choose any numerical solution of algebraic equations like Gauss-Seidel method, Thomas algorithm, LU factorization, whatever it may be. So next, how we implement these for any order of the differential equations. We can, I explained taking with second order linear ordinary differential equations, step by step, how we find the solution, how we correlate with exact solution, what kind of what kind of error, how we are going to increase the accuracy, taking different types of basis functions, different types of the collocation points. If suppose when it comes to PDE, how we are going to implement it. If suppose we are going to deal with non-linear differential equations, how we convert into linear differential equations using quasi-linearization method, which is developed based on the Taylor series. And for coupled equations, how it can. So this is the basic algorithm, and now this is the end of the lecture. Yes, these are a few references. Over to the organizers. Or suppose before that, any questions, queries, doubts, you please raise.
Sir, feedback, sir.
Yes, sir. Yes.
Sir, you
Hello.
don't worry about feedback, sir. There is no feedback, sir. No
No,
problem.
any,
Other
any,
than
any.
that, please ask doubts regarding the subject, sir, to the expert, sir. Thank you.
Yeah, yeah, yeah.
If anybody have doubts.
So, sir,
Yes, yes, sir.
for
Go ahead.
non-linear problem, for this non-linear problem, you are using only the basis solution as monomial basis function.
Yes, correct.
Okay, if we use the next next
Lagrange
Lagrangian,
polynomial.
that means
Yeah.
the process will be slow, or what will
No,
happen, sir?
the process means with respect to execution of the code. Yeah, with respect to the execution of code, it won't take much time. Maybe 10 or 20 seconds, maybe extra. Or if suppose you are taking 200 collocation points, it all depends on how many number of points you are taking. If see our problem accuracy requirement is only 10 power minus 5. That can be obtained with only 20 collocation points. But I want to increase 200 collocation points. Just think it. Whether it is really necessary, not required. With a 20 collocation point itself, we are getting the required accuracy 10 power minus 5. You take that only. Or you can take a little nearest value, maybe 30 points. That is fine. And you are telling that
Yes, sir.
Lagrange
Thank you, sir.
polynomials,
Thank you, sir.
Lagrange polynomials, it won't take much time. Yes. Next, further.
Thank you, sir.
Yes.
Okay, any more? Sir, okay, thank you very much, sir. I think
Yes.
no one is there. We are very happy to from you, sir, to listen that. Very nice
Yes.
session. Also very motivated, sir.
Yes.
We are very much thank you for you, sir.
Yes. Yes.
Okay, okay. Please, anyone, please arrange roles. I'm going to close the session. Okay, I think, sir, no one is there, sir. Sir,
Yeah. Yeah.
with
Fine.
with audience request, I am asking from my side. If you send the PPT to me, I'll share to them, sir.
Yeah. Yeah. There are some corrections, right?
Okay,
I'll
sir.
change
After
those
that, I will
corrections
check.
and forward. Yeah.
Okay, sir. Okay,
Yeah.
thank you very
Okay.
much, sir.
Okay. Okay.
Okay, sir. Hi, every participants. Don't worry. After obtaining the PPT from sir, I will post to you in the WhatsApp group. Thank you, very well. Thank you. Bye.
Thank